All right, so today our colloquium is by Shaela Jones. Shaela is a research associate with Goddard Space Flight Center and the Catholic University of America. She received her PhD in physics from the University of Maryland, and her current research is focused on images of the solar corona to enhance coronal magnetic field modeling, and that's what she's going to talk to us today about. But she's also done work related on coronal rotation, tomography, and plasma bombs. But today, magnetic field.
Okay, they told me to stand over here, so I'll do that. All right, so thanks for giving me a chance to talk to you guys today. I'm here to talk about this new method that we've developed for using coronal images to improve coronal magnetic field models, and we call it image optimization. It's a little shifted, but okay. That's right, that's right. Hopefully it'll be okay. So basically, I'll start by talking to you a little bit about how and why we do coronal magnetic field modeling, and then how we can use coronal images to help with that. And then I'll show you some testing that we did of the method that we developed, and finally I'll show you some applications that we did with K-core data. So first off, coronal magnetic field modeling. Basically, it's hard to measure the coronal magnetic field, and I think probably most of the people in this room know that. Because it's really hot and it's very dynamic and it's optically thin, and typically if you get measurements, you're mostly going to get them in isolated regions. And so this is an example of some work done by Maxim Kramer in 2016, where they tried to take comp data, which, as you know, is a line of sight integration of the magnetic field signal, and they tried to tomographically reconstruct the coronal magnetic field. But in order to do that, they have to also tomographically construct the density and temperature structure, which introduces an extra source of uncertainty. Okay, so when you want to do a model of the coronal magnetic field, which is sort of what you're left with, you have to start with the photospheric magnetogram, okay? And since we can only see one side of the sun at any time, you take a whole bunch of these full disk images, and you can combine them over the course of a month to come up with a map of a synoptic map of the coronal magnetic or photospheric magnetic field. And then ultimately, you can make some certain physical assumptions and use that photospheric measurement as a lower boundary condition to extrapolate out into the corona and ultimately out into the heliosphere. So this is just an example of a bunch of magnetic field lines traced onto an AIA image. There's several different models that are popular for people to use when they're doing this kind of modeling. The PFSS model is probably the oldest, and it's the easiest. So it's fairly common still today, even though it has some limitations. It's nice because it does produce a unique solution. Basically, the idea is that you have the value of the field at the surface, and then you assume that at some point out, some spherical shell out in the corona, the field becomes purely radial, and it just extends radially out into the heliosphere and then forms this beautiful ballerina skirt. And in the meantime, in the interim, you're assuming it's a current-free corona. And so obviously that has some limitations in terms of physical accuracy. Or you can get more, a little bit more involved. You can do a nonlinear force-free field where you're assuming there are currents in the corona, but you're only allowing them to flow parallel to the field. And the problem with that is, well, there's a couple of problems. One is that it's typically difficult to apply to a large area. You don't generally construct global nonlinear force-free field models. And there are some issues with the lower boundary condition. You can get inconsistencies in the photospheric magnetogram that cause problems with your modeling. And so different groups have different ways of constructing the models and different ways of pre-processing the magnetograms. So you don't get that nice, unique solution. And then you can go with a full MHD model, which, again, you're getting more physics, but you are still having, you're having issues now with trying to resolve all of the relevant scales. And it's a very resource-intensive model. So how do we do at this? How well is it going? And this was from a paper by Pete Riley and co-authors where they tried to compare synoptic maps from different observatories. And he was trying to find some way to convert between at least one observatory and one other observatory and try to see, okay, if we can get agreement between at least two of them, then we have some idea what is the truth, what is the true photospheric magnetic field. And his conclusion at the end of the study was that there is no ground truth that he could find. He found some consistent or some significant differences between the different observatories that varied with the solar cycles. You couldn't you couldn't develop a standard method for converting between any one or any pair, and that those differences have a substantial effect on the modeling outcome. And this is a study by Lanjian from Goddard. She was comparing, so there are different observatories you can use to get the photospheric condition, and then there are different models you can use to extrapolate into the field, and she was sort of comparing the results from all the different combinations of observatory and model that you can get through the CCMC. And her conclusion was that the model results are really sensitive to the magnetograms and the models, and that it's hard to find a combination that was consistently superior. She would find that sometimes for a little while one model observatory combination would be superior, and then all of a sudden it would switch and that one would perform poorly. So what we wanted to know was, is there any way to use, we have a plethora of coronal images, can we use the coronal images to improve the situation with the modeling? And, you know, this was sort of driven by the fact that when you look at images of the corona, you can definitely see what strikes you as magnetic structure. And so how can we use that information? And if you take just a little point on the image and you draw a little line that sort of seems to be parallel to the magnetic field, and then you can do that again and again and again until you get really tired of it, and then you ask a talented colleague to come up with image processing software to do this for you. In our software, we use constraints that are automatically generated by some software created by Vadim Uritsky. And then you can look at the point in the model that corresponds to that location on the image plane. Sample or interpolate what is the magnetic field at that point and project it onto your image plane and see, okay, what is the slope of that projected magnetic field line on the image plane or from the model, and compare how well does that agree with what you see in the image. And that's the basic idea. And in order to quantify the degree of agreement, basically we take these angles that we measure on the image, the slope of that little line, and we compare it to the angle that you would get from the model field. And you construct this objective function J. So basically the bigger J is, the worse the agreement between the model and the images. And that allows us, at the very least, to compare different models and say, okay, model A, B, and C, which one agrees best with the images? But we wanted to go a little farther than that. We want to actually, so the real problem is that there's not enough information from that synoptic map of the photosphere to reconstruct the entire heliospheric magnetic field. And so what we wanted to do is see if we can incorporate some of the images from the, some of the information from the images into the model. Sure. Well, yeah, that's a good question. So what we do is we primarily work with polarization brightness images. And so we assume that everything we see in the image actually lies in the plane of the image. It's the plane perpendicular to the observation direction that intersects the center of the sun. I'll talk more about that. Okay, I promise. And then we did something that people find even wackier sometimes, which was we decided, well, if we know that the magnetograms are not perfect and we don't know which of our observations, if any, are actually consistent with the real photospheric field, what if we treat those synoptic magnetogram measurements as a parameter that we can optimize, that we can change in order to get better agreement with the images? So this is kind of a cartoon of what we do. We start with a synoptic magnetogram, and we use that to calculate a magnetic field model, and we compare it to what we see in the images via that objective function J that I described. And then we use an optimization algorithm to repeatedly alter the magnetogram, see if you extrapolate a new field, and see if you get better agreement. And ultimately, the product of that process is an optimized magnetic field model, and what I call in air quotes an optimized magnetogram. And one additional detail about the way that we do this, we actually, when we first started doing this, we would work with fairly coarse resolution magnetograms, and we would optimize the value of the flux in every individual pixel of the magnetogram. And then we quickly realized that we wouldn't be able to do that for any kind of interesting resolution. And so what we decided was, instead of optimizing each pixel, we would take the spherical harmonic transform of the magnetogram and optimize only the lowest order coefficients of the transform. And the idea with that being that we can make large-scale changes to the field without having to optimize a very large number of parameters. And it's nice because our focus, of course, was always to get better heliospheric predictions. And these lowest order components that you find in the transform, those are the parts of the field that extend out into the heliosphere. And so if we can't get every tiny little detail of the magnetogram right, I'm okay with that. What I want is to get the large-scale field correct. So we decided to try this out. This is from a paper that we published in 2016, where we first started working with this optimizing the transforms. And what you're seeing in the top row is we took a gong magnetogram and created a PFSS extrapolation from it. And we treated that as the true magnetic field. And we sampled artificial constraints from that model. Then we perturbed the magnetogram to produce this field that you see in the middle. You're looking at this from 3 different perspectives. So you can see we made a substantial change to the field by perturbing this magnetogram. And then we fed that perturbed magnetogram and the accurate constraints into the software to see, can the software force the magnetogram back to the original configuration? And if you compare this bottom optimized row to the original row, you see actually we were very successful with this, and we were really pleased with that result. Sure.
So you got something similar to what you have from tracing white light, I guess. So what would you actually see?
So in this test, we actually literally went into the model and sampled the magnetic field in 12 image planes that were equally spaced around the axis, the Z axis, and they're evenly spaced in longitude and radius. And so actually when we did the second paper, we said that's not very realistic for what you would get from a coronagraph image. So for the second paper, we started creating artificial constraints that were clustered around the streamer belt and were clustered closer to the occulter, the artificial occulter. And the other thing that we did was, well, what if our measurements are noisy? So in the first figure here, we were saying, well, what if you didn't do a very good job on those angle measurements? What if you were a little bit off? And in the first one, this is that perturbed magnetic field. And next to it, you see the ideal that the software is trying to get back to. And we've now using the artificial constraints that are clustered from the streamer belt from the areas where you'd have a lot of observations from the coronagraph. And then figures C through F, you're just adding more noise to the accuracy of those measurements. And what you see is that you do get a slight degradation. So this is going up to 20 degrees standard deviation, which I think is more than I would expect from our image processing software. And then the other question that we had was, well, what if we're not right in assuming that everything's in the image plane? So what if the constraints that we pick, what we did was, instead of creating the artificial constraints by sampling from a single image plane, we sampled constraints that were scattered around the image plane to some extent. And so figures C through F here are showing you increasing amounts of scatter around that image plane. And what we found was you can definitely see degradation in the result as you add more scatter, but you're still doing considerably better in matching the ideal field than what you started with. Yeah. I think so. I don't think I would. Right. Yeah, so that's an interesting question, because if you think about the spherical harmonic transform, you can't constrain anything that's not axisymmetric. So it depends on how many of those transform coefficients you're trying to do. I think if you had two image planes that were, say, off by 90 degrees, then maybe you could constrain, say, the dipole moment, that kind of thing. But I think the reason that we picked 12 was that we were trying to go up to L equals 6. So then we said, all right, we like the results from the test, but there's nothing like trying it on real data. So we chose to work with K-core data for this because it's got a nice low field of view, and we're comparing to the PFSS model, which people generally have close around 2.5 solar radii. So we picked a period, for historical reasons, we picked a period that the Earth was near to the ecliptic plane, and when there were a lot of observing days from K-core with very few CMEs. And we took one image per day for this time period, 16 to 29 of November. And this is just a look at the performance of the optimization algorithm. This is a plot. You can't read the axis, but this is a plot showing you how much the objective function value at the best known point is tracked through the computation time, basically, over the course of the computation. And as you can see, it kind of falls off very rapidly, and then the improvement slows quite a bit. And that's generally the sort of pattern that we look for. If you saw like a nice linear decrease, that would probably be a bad optimization. So this optimization is probably really done at 4 minutes, but we don't currently have a criteria for shutting it off when this slope decreases so much. But I've run this as long as an hour, and it basically doesn't get better after this. On the right, this is showing you, so these angular differences here are what we refer to as the residuals. And this is showing you the distribution of those residuals. The dotted line is the distribution before the optimization. And so you see that we have residuals that go up to pi over 2, basically where the constraint and the model were perpendicular to one another. And then the solid line shows you the distribution after, and you can see there's definitely a clear improvement, even though we still see these constraints that are completely unmatched. And I think that's always going to be the case because we are trying to match a real corona with a very artificial model, and because our constraints are never going to be perfect. So this is a comparison of what the field model looks like before and after the optimization. And I want to caution you not to pay too much attention to what happens to these low-lying loops because we're not able to constrain those with the chronograph images. We'd like to add some lower constraints in the future, but for right now, what we're looking at is the large-scale field. And in particular, what we notice with this is that the field has a lot more open field lines than it did before the optimization. And the coronal holes sort of extend to lower latitudes. That's the main difference that we notice. And then a lot of people ask, well, what actually happened to the magnetogram? Has it changed a lot? And so this was done with gong magnetograms, where the dynamic range is typically something like negative 400 to positive 400. And this is showing you the change in the magnetogram due to the optimization. It's basically on a scale. So you can see the scale negative 10 to 10 Gauss. It's a fairly small change, but it happens over a large area, so it has a big effect. And it looks kind of like what you would expect from adding together just those first L equals 6 and lower terms of the transform. You get a very wavy correction. Now I have to give you the caveat that if you think about if you took the magnetogram and you did perform the spherical harmonic transform and then you performed an inverse transform, you do get a lot of change in the like the very, very high flux regions, because when you perform that transform, you throw away some information. So any very sharply spatially defined feature, once you do the transform and then the inverse transform, is kind of blurred. So the high spikes kind of get damped down and you get a little bit of ringing. So this is just comparing the optimized magnetogram to a magnetogram that's been transformed in inverse transform. Yeah, it was fairly quiet. This is 2014, late 2014. I see. Did I show the magnetogram? Oh, you mean in the change? Yeah, it's hard to tell from that perspective, but yeah. I think the median change for this was like 1.9 Gauss. And the average was I'll take your word for it. Yeah. Okay. So this was the next time period that we chose to study. It's from May of 2016. It's a similar data set. You can see there's a lot of days with no CMEs and a lot of observing. And again, we just chose one image per day and processed it. What was interesting was when Vadim did this data set and he sent it to me, he said, the images seem different. And so there aren't as many constraints. But when I looked at the results of the optimization, I said, you know what, I think the images are better. Because, so again, we have this like nice, clear improvement, very rapid improvement at the beginning and slow improvement later on. So that's good. That tells me it's a good optimization. And this time, we actually saw, I think, I would argue, more improvement in the distribution of the residuals as a result of the optimization. And so that's why I think they may be better quality constraints. Okay. All right, well, now you have proof if you want it. So this is comparing the hairy ball images of the field before and after optimization. Once again, the main thing that we notice, I'm a little bit disturbed by this, the way this, whatever this feature is, sort of swings a little bit farther west than it used to. But again, we notice that the field is a lot more open field, magnetic field lines. And it's actually hard to see from this perspective. This happens to be the perspective that Earth was looking from at the time of that data collection. But if you look at this limb here, and then you look at this green over here that's appeared, that's another coronal hole that's significantly larger than it used to be. So basically, to tell you what I told you, we made a technique to incorporate morphological information from the coronal images into the models. And we've tested on a couple of theoretical problems. And so now we're trying to make our first results to real data, our first application to real data. But we need more constraint sets. For one thing, I really want to know, how we have two data sets, and in both sets, I see the corona opening up a lot more. And a lot of modelers, when I go talk about this, a lot of modelers come up to me very excited because they would like to see a more open coronal field. They're convinced that the measurement of the polar field is weaker than it's supposed to be. So I'd like to know if that's a general trend that we're going to see in a lot of data sets, or if we just got lucky with these two. And also, is there any solar cycle variation? Certainly there's solar cycle variation in the quality of the constraints that we're going to be able to get from the images, the distribution in latitude. And then I'm particularly interested to know if I see a particular change to the magnetogram in one Carrington rotation, would I see the same before and after in the adjacent Carrington rotations? Additionally, I like to include more kinds of image constraints. And so we need more flexible image processing software. And eventually, we'd like to do this with more models than just the PFSS. And of course, when we started working on this and we were working with optimizing individual pixel values, there was a lot of excitement about active regions that emerge on the far side of the sun because they don't show up in the synoptic maps for sometimes a couple of weeks. And so we would like to kind of get back to doing something like that, but we're not quite sure the right approach yet. So thank you. That's it. Yes.
So very interesting. And we were thinking about the polar fields. You showed that one kind of concept where you had the difference in magnetogram.
Right.
It was kind of hard to tell from that projection what was cold and craters. Are you seeing more change in the polar fields, or where does this?
Yeah, not so much. I mean, so this is longitude versus latitude. I'm sorry, it's really hard to read there. And so I can't actually tell if this is far from zero, but I'm going to say it's probably not. in terms of how much it changed. And this was from the 2014 data set, which happened to happen at a time when there was a really weak dipole field. And so I don't know if I would see a bigger change in the polar fields at a time when the polar field was bigger. I should say that so I had a problem when I first started working with this data set where the optimization early in the process, it inverted the dipole moment. And then the constraints don't care if the field is going in or out. And so it had no way to force it back to, the correct orientation of the dipole. So after that, we started taking a set of Carrington maps from around the time of the one we were optimizing and figuring out what's the range of each spherical harmonic coefficient during that time range. And we now force the model or the optimization to try to look for a solution in that range of possibilities. So if the dipole moment was quite small during that time period, it would make sense to me that it doesn't change the dipole very much. Yeah.
So you start off with a Magnetogram, use a PFSS model, and then pair that with your Coronal populations. And then you, for example, the Magnetogram, use the PFSS model. So the Magnetogram in the first place could be wrong. PFSS model, which I kind of didn't even think of for the largest energy. And then with the Coronal and data itself, and do you have any feeling of which of these three things is causing the biggest uncertainty?
Yeah, it's a good question. I think Sarah and I actually talked about this at the AGU one year. I don't know. I do know that when I look at the constraints that we have, I really am very uncomfortable with the constraints that are very close to the source surface, because the coronal magnetic field, when you look at an image like this eclipse photo that I showed, you can see there's actually like a lot of field that is not closed at 2.5 solar radii. So as you get close to that boundary region, your constraints are going to be telling your optimization software, keep going, I want this to be more open. And your model is going to keep saying, no, it has to close before 2.5 if it's going to close. So I don't know. It's a really good question. Yeah.
Following up on that, could you you're right now setting up some change in the lower boundary. Could you change it, set it up to optimize for the source surface height as well?
Yeah, that's something that John Linker brought up too, actually. So I've tried looking at running the optimization with different settings of the RSS, but I haven't tried optimizing it. It's interesting because that's a really different parameter than all the other parameters I'm trying to optimize. So I think that's why I'm a little hesitant to throw it in the mix. Yeah.
Back to that comment about Magnetogram being wrong. The Magnetogram is correct on the Earth-facing side. It's the synoptic map that's generally wrong with certain instances.
Sure.
So that's agreed upon major source of error in the model. So two ideas. One, you could weight more heavily on optimizing the visible side, because you shouldn't be changing the downside that much.
Right. We tried doing that with, okay, so in order to do that, you have to have some way of quantifying how reliable do I think this pixel in the synoptic map is. And if I can do that, then I can add a term to that objective function that penalizes changes in the magnetic field, but it allows you to weight the penalty for different pixels. And the only source that I could find for an estimate of that reliability was the folks who make the adapt maps had some sort of, they tracked for each pixel how long has it been since this pixel was updated. So I tried doing it with that and was not very successful. I don't know if it's because I'm optimizing the transform space and it just can't only change the ones on the backside. But
You're doing it for one synoptic map at a time, right?
Yes.
Could be. Well, it depends on how the synoptic map is made, right?
Well, and can you create a big change on one side of the map without changing the other side of the map if you're doing it from adding together so few terms? Yeah.
And given the magnitude of your changes there, like I said, you're pretty close to the light bulbs. So really what's happening here is you're just redistributing flux in ways. You're not really adding flux.
Right, no.
Noise levels in magnetogram. You're redistributing it around the sphere to optimize
Yeah. Yeah, I actually have an optional term in the objective function that allows me to penalize if some net flux has been added. And I find that I don't really need to use it. It doesn't want to add flux or take away flux. It just wants to redistribute it, like you're saying.
That's only going to be really reliable in cases where you don't have a major activation on the backside.
Right.
In those cases, no GSFC models optimize.
Well, I think it depends. I mean, when you're looking at just the coronagraph images, when a new active region emerges, sometimes it has a big effect on the large-scale corona, and sometimes it doesn't. It sort of depends on where it's placed. If it's really close to the boundary between open and closed magnetic fields, then yeah, you see a big change. But sometimes you don't. Oh, well. Is he here? Okay, good. Did you have a question? Yes. So that's sort of what this wiggly plot is. This is the difference between the original magnetogram and the optimized magnetogram, taking out all the parts that are the result of transforming and inverse transforming. Oh, before optimizing. Okay. I don't think I'm understanding your question. Uh-huh. Uh-huh. Yes. Yeah. I see. Okay. Yeah. And you definitely do see differences. You do see differences. Like there's not only are the little spikes sort of damped down, but also you see some ringing. You can use different methods for calculating the PFSS model that sort of reduce the ringing, but I have not yet tried that. Go ahead. For these ones, I think I ran it with 120. It was from a gong magnetogram, so it's got 360 resolution in the longitude direction. Okay. Do you have another question, Sarah?
I was just going to ask if you compared to other magnetograms with the same rotation.
That is a good question. So not this past year, but the year before that at the AGU, I presented about this, and one thing that was really bugging me at the time was when I ran the optimization with one observatory and with the other observatory, I wasn't getting more similar results than what I started with. Now I think it has to do with the fact that the PFSS calculation that I'm doing is not doing a very good job sampling the high resolution HMI magnetograms. So I need to come up with a way to deal with that, and then I think that's a good idea.
Juliana and I have talked about this recently.
Okay. Anything else?